A microwave cooker uses electromagnetic waves of frequency 2450 megahertz. The microwave warms the food in the cooker by causing water molecules in the food to oscillate with a large amplitude at the frequency of the microwave. Large amplitude. So when something oscillates in an extreme pattern, when something oscillates in an extreme pattern, what it may be?
Resonance.
Resonance. Actually, resonance is a phenomena where you can have the oscillation reaching a very high amplitude. The effective microwave power of cooker is 750 watt. The temperature of mass of 280 gram of water rises from 25 to 98 in a time of 2 minutes. Value for the specific heat capacity. So if we use the heating formula, mass is in gram, but the answer is coming in kg. So share this working.
Uh, 4400. I've rounded it.
4200.
No, 4400. 4400.
Okay. This is a rounded value.
Yeah, the original value is 4403.1. So usually they round it right to pretty significant.
4403.1.
Yeah, 4403.1.
The value of the specific heat capacity determined from the data is greater than the expected value. It means examiner says that this is a type of overestimation. A student gives as the reason, gives as the reason for this difference heat loss to surrounding. Suggests in more detail that given by the student a possible reason for the difference when heat is lost to the surrounding. So will you have to heat for longer or less time?
For longer time?
For longer time. So heat loss to surrounding. Longer time. Time is in the denominator. Sorry, in the numerator. So greater value of C. So C will be overestimated because you need more time because heat is being lost to the surrounding. June 15, 1541 to state what is meant by internal energy, the definition. It is a sum of a random distribution of kinetic and potential energies Do you have this question?
No, sir.
This is a definition. Now, this is a very famous question. This type of questions are called cycle questions. The variation with volume of the pressure of an ideal gas as it undergoes a cycle ABCA changes is shown. Now, there are two types of lines in this cycle. Horizontal line means constant pressure. Vertical line means constant volume. While curve means both volume and pressure are changing. Temperature of the gas at A is 290 Kelvin. The temperature of B, the temperature at B is 870 Kelvin.
Zero 0.199, so you can write it as 0.2.
0 point.
It's 0.199, but we can write it as 0.2.
Temperature of the gas at C. I have volume A to C. Pressure is constant. So we are moving from C to A. Pressure is constant. Volume is changing. He wants to have a temperature at T. So I can keep the mole. I can keep the mole the same because I should assume that it's a closed container. So C to A, I want to find the temperature at C. So at C, I have the volume. At C, I have the pressure. I have the number of moles. So I can rewrite the formula. Pressure is the same, 1.2. What is the volume? Going in between. Here.
Can we take it as 7.75?
Right. I think the same, 7.75. Get the temperature.
$5.59.
Explain why the change from C to A involves external work and a change in internal energy. So I have already marked here. C to A, pressure is constant, volume is increasing, so there must be some work done. So I will try to convince examiner that, look, C to A, volume so work done is justified. Now, can you help me in writing the concept that how I can say that internal energy is also changing?
So temperature decreases from C to A. So internal energy will also decrease.
Decreases. So can you repeat the concept, what you were saying?
I was saying that the temperature have decreased, so from C to A, so the internal energy will also decrease.
The change. But perfect. But you have to convince the examiner. You have to tell him that delta U is only a function of delta EK. delta EK is coming from temperature. C to A, temperature is increasing, decreasing. C, temperature was 290 at A. At A, and
C
then
to A, it's decreasing.
hmm, this is the way you can write it. Let's see if you have this paper. June 15, 41, 3. Define specific latent heat. Look at this definition, and you have to, just like as I have written, so keep on writing whenever you get a chance. Writing helps to memorize the definition. An electric heater is immersed in some melting ice that is contained in a funnel as shown. The heater is switched on, and when the ice is melting at a constant rate, the mass of ice melted in 5 minutes is noted. Together with the power of the heater, the power P of the heater is then increased. A new reading for the mass M of ice melted in 5 minutes is recorded when the ice is melting at a constant rate. Data for the power and the mass M are shown. Mass M melted in 5 minutes. So I'm trying to do this working. Now,
0.26 and 0.38.
use the data in the completed figure to determine a value for a specific latent heat of fusion L of the ice. Pt is equal to ml. So he's using L, capital L. Just a minute, you complete this calculation, just a minute. Did you try this question?
Yes, sir.
So what answer you are getting?
333.
The rate h of thermal energy gained by the ice from the surrounding. How we do that? The rate of thermal energy gained by the surrounding. So rate of thermal energy means thermal power. Have you done the same calculation for part 2-1 or you have done something different?
I did it a bit different. I took both the power values and subtracted them, and I took the
Why
both of the
subtracting?
mass value. Because we have to use all of them, right? So I thought we can subtract.
With the power of the heater is then increase a new reading for the mass m of ice melted in 5 minutes. Subtracting. Because when I'm calculating this 70 upon 0.26, I'm not getting 333. What the reason for subtracting? How much comes when you divide 70 by 0.26 divided?
269.
It's coming wrong. What is the reason for subtraction? There must be some reason, na? Because we have power 70. So he says that mass m, he is subtracting the mass melted per second, 0.26. So we're not using 78. Then this is the possibility here that actually at 70, the mass melted per second is 0.26. And at 110, the mass melted per second is 0.28. So the possible reason for subtracting is the change. The power changes from 70 to 110. So the mass melted per second changes from 0.26 to 0.28.
Sir, it's 0.38, not 28.
0.38.
Yeah, for that one. Yeah.
Sure. Because I thought you said 0.28.
No, I said 0.38.
Okay. 0.38. First, I should correct this. Sorry, actually, my standard is not working. The power changes from 70 to 110. So the change in power 110 minus 70 is equal to 7 point, you said point 38 and 0.26. The rate h of thermal energy gained by the ice from the surrounding. Rate of energy means power. The word rate of energy transfer is for power. So how should what at what logic we should do that? We have the value L, rate of thermal energy gained by the ice from the surrounding. So we can use Q is equal to, acha, delta temperature is constant. So now, did you try number two?
No, sir, I'm stuck.
So you have to see this idea that it's a power, and the power you are transferring, 70 is the power. He says there is a concept of energy loss to surrounding. He says data for the power and the mass are shown. So we should remain that if you remember this topic, I had explained there also, when you are heating from a heater, actually you are getting heat from the surrounding also, because when you are melting something in open environment, definitely you will be getting heat from the surroundings. So agar if you look at this apparatus carefully, the ice is being melted by two sources of heat. One is the electrical source and one is the surrounding source. The common sense approach is there. If I switch off the heater, ice will still continue to melt as it normally melts. How ice will be melting even if you have switched off the circuit? Why? Because there is no external power, but there is external heating, the environmental heating. So now you have to tell examiner that actually heat is coming from the heater, heat is coming from the surrounding. So if I make the logic of this answer, I will say that heat from the heater plus heat from surrounding, together this heat is going toward ice. So it means that you have to sum up the heat, and when he says rate of energy, so actually he means to say power. So when he says that you have to find the rate means power. So I have made the idea, heat from the heater plus heat from the surrounding, they together are melting the ice. He wants to find the rate of thermal energy transferred by the ice from the surrounding. So he wants to find actually the second bracket, heat from surrounding. So I will do one thing, that now I have to first understand this thing, that the heating here, look at this mass m heat melted per second. This is not alone by the heater. This is the overall effect. This is the overall effect of the heater and the surrounding. So I have to understand one thing, that this number 0.26 or 0.238, this is the combined effort. This is the combined effort of surrounding and the heater. Now we can make the working. And the same approach, that you have to find the two powers and then you have to make the time factor. Total power into time is equal to ml. Okay, let me call power of heater plus power of surrounding into T is equal to ml. So power of heater plus power of surrounding is equal to m upon T into L. I have made an equation. Now you have to help me out. But I can take any line. If I take the first line, the power is 70 and the rate is 0.26. So I can take 70 plus power of the surrounding is equal to rate. M upon T is 0.26 into 30. So now you have to solve this.
Uh, 1.2.
1 point. Can you please repeat? 1
Coming
point.
as 1.2, but isn't it a small value?
It's a very small value. But how come you're getting such a small value? Because
Wait,
70,
one second.
70 will go there and subtract.
1 second, silence.
Maybe you're dividing.
It's 15.8.
15 point.
8.
So that was a tricky question, but it helped us to understand a very important concept which we were discussing in our theory also. So, well, let's keep it up to here. And we did some questions today and we will inshallah continue in our next class. Allah Hafiz.
Thank you, Sir. Allah Hafiz.